Today, what I want to talk about is this topic that I've sort of been exploring in a bit more depth. And there's a couple of papers about this topic that I want to cover today. But the main theme of today is going to be like compilers for machine learning. So what do we mean by that, right? So if you're writing some sort of like a neural network in a library like PyTorch, like maybe you would do something like this. Like you'd say, well, I have my network, right? And then this inherits from like torch dot module, right? And then basically to get this thing to work, what you need to do is have an init function. And then in this init function, maybe you'll have something like self.layer1 equals layer1. Self.layer2 is equal to layer2. And then the main thing you really need to do to get this whole thing working is this forward function. And in the forward function, what you're going to do is you're basically going to say, well, like I have some sort of x, right? And then x is equal to layer 1 of x. And then x is equal to layer 2 of x again. And then maybe like fully connected is equal to fully connected of x. And then you get like some sort of logit, right? And then you say something like return logit of x, right? So this is like, let's say something like logistic regression with 2 layers. And so this is sort of like what you're doing, right? And so what you worry about as a user for this stuff is like typically you'll worry about like you'll worry about basically like test level performance, right? So basically I'm gonna say like as a user, you worry about like, let's say test level performance, explanations, like ease of use, or maybe like not really, right? So basically what I mean here is like your metrics are like by test level performance here, I mean stuff like one, I mean accuracy, precision, recall, like sort of depending on what your use case needs. However, if you're a library maintainer, or by library maintainer, like I actually mean like the PyTorch or Tensorflow maintainer, then you sort of worry about a different set of things. Like, so you sort of worry about basically make the model, like basically one I would say is like the library has to be like usable, like user-friendly library. So this is sort of the forward-facing stuff. But then there's also the backend that's really important, right? And so by backend here, what I mean is like stuff like basically does the model run fast? And this is really what we're gonna talk about today. Like how do you make it so the models run fast? And there's sort of two aspects to this question, right? So does this model run fast? One is basically what I'm gonna call like single machine perf. And then basically multi-machine perf. So here what I mean is that like here essentially we're gonna have some sort of intermediate representation for models, VM, to make sure that this runs quickly. And then as far as the multi-machine perf here, like what we're worried about is basically distributing a model on multiple machines. And this is also sort of a tricky problem, but like let's sort of unpack this problem a bit. So let's assume here that the sum of layer 1 and layer 2 don't fit on a single machine, right? So let's say layer 1 is about 40 gigs in size and layer 2 is about 40 gigs in size. Now this is not going to fit on any GPU. So what you would do instead is you say, okay, great. Well, I want to run this thing on device number 1. I want to run this thing on device number 2. So this could be like one way of distributing your work. Another way could be to say, well, okay, well, what I want to do now is actually I want to split layer 1 into 2. And then what I'll then do is concatenate them. Or you could say, okay, well, maybe there's like some sort of other kind of layer that I could add here that compresses this further. And so the sort of set of tricks basically is a whole body of research. It's not a body of research that I see gets a lot of attention in academia typically, because most ML practitioners are not compilers engineers or think like compilers engineers. But there's a couple of papers that are really excellent at this topic. So now that we've sort of introduced the problem, let's sort of take a deeper dive and see how this stuff actually works. All right. All right, let's start with MLIR since we mentioned that already. So, like the first thing you'll notice here is like who the first author is. So, Chris Latner was the inventor of LLVM, and like a big part of LLVM was supposed to be like, well, you could write like code in any language that you want, but once it gets compiled down to LLVM, then you can run it really fast. And so the idea was LLVM could just like you could have like an easy story to create compilers that transpile your language from to LLVM, and then the LLVM compiler itself gets a lot of work. So the MLIR work is fairly similar, and you can see here there's like a whole bunch of people at Google that worked on this as well. And I will also mention that I think Chris is no longer at Google at this point. I think he started his own company on using RISC-V compilers, and so basically, I'm just saying like this is like if you do want to read a paper about ML compilers, it's probably one of the best authors that you could start with. So MLIR aims to address software fragmentation, improve compilation of heterogeneous hardware, and significantly reduce the cost of building domain-specific compilers. Yeah, so let's like go back here for a second, right? So basically, if essentially when you're doing some sort of PyTorch programming, right? Like what you're also doing is like, let's say you say, you know, like this model, this function doesn't exist in PyTorch, but let's suppose it does for a second, right? You'll say something like, you know, my network is equal to my network, right? And then you would basically say my network and then something like GPU, right? So, but what's sort of involved in a function like this, right? So if we were to sort of unpack this a bit, then what run model would do is say something like, well, let's say, you know, like, so it has the network and then it has the input X, right? And then so let's say input, let's say it's going to be model X device, right? So this is what this is typically going to look like. And so what you're going to come in and do here is you're going to say like X to device, device, right? And then model to device, device, right? So this is your prediction. But then to basically read your to basically read your prediction back on the CPU so you can print it at the console, you're also implicitly saying the device CPU, right? And then you're saying something like return. So there's a whole lot of stuff going on here, right? Like one could be, well, like even when you say the to device function, there's like a whole bunch of stuff here involved, right? There's like load balancing, there's scheduling involved, there's maybe some profiling involved. And so basically my point is that like a lot of times that we use these libraries thinking like they're just like these really simple things, but often it's actually quite involved, I think, what generally happens here. And even just saying like I want to run something on a GPU, sort of is actually an ambiguous statement because you're always returning stuff back to the CPU. So figuring out like what is being sent and what isn't, you know, there's exceptions to this, like, right? Like let's say, for example, define run model was actually something closer to this, like model X device and then embeddings, right? Embeddings are actually very large. So basically with embeddings, you would just say to device CPU, but then the X to device GPU. So just basically based on the kind of data that you're sending, you would send it to a different device. So this is just important to think about, and like I guess not something we generally think about when we're programming these things. Where is it? There it is. Sorry. All right. So MLR facilitates the design and implementation of code generators, translators, and optimizers at different levels of abstraction and also across application domains, hardware targets, and execution environments. Yeah, this is a back to this example here, right? Like when you say basically to divide, like when you say GPU, right? Like this is not a this is also ambiguous, right? It could be AMD, it could be NVIDIA, but then it also differs the type of GPU. So there's all sorts of stuff going on here, and the code just seems to work fine across them, right? And that's not by accident. So the contribution of this work includes discussion of MLIR, uh, semantics, and evaluation of MLIR as a generalized infrastructure that reduces the cost of building compilers, and describing use cases to show research and educational opportunities for future opportunities. So compiler design is a mature field with a wide known and well-ranged application for code generation. LLVM, single abstraction level to interface with the system. The LLVM intermediate representation is roughly C with vectors, and JVM provides an object-oriented type system with the one-size-fits-all approach is incredibly valuable. Interesting. LLVM and Java. Okay, yeah. So let's talk about this for a bit. So basically, this idea of what did they mean again? Like this is sort of again basic CS, but it's important. Like when you the advantage of a virtual machine is that it abstracts away the machine itself. So you don't really need to, you as yourself, the programmer, worry about how this works on a specific machine. Only the person developing the actual hardware needs to then worry about how does this actually work with let's say the JVM or the LLVM. What's interesting, when you say something like C with vectors, this says something really specific, right? Like what this is really saying is C with good numerical computing, because that's really what vector computations are all about. Oh, hey Krishnan, how's it going? So at the same time, many problems are better modeled at a higher or lower level abstraction. The many languages include and Swift develop their own languages for linear types and to improve the implementation of the lowering process. And typically, machine learning systems use ML graphs as domain-specific abstractions in the same way. Okay. In the box infrastructure to solve common compiler engineering problems by standardizing the static single assignment-based IR data structures, providing a declarative system for defining IR dialects, and providing a wide range of common infrastructure, including documentation, parsing, printing logic, location tracking, multi-threaded compiler support, and path management. Okay, I hope they'll explain all of this stuff a bit later. It's going to lead to lower quality compiler systems, including user-visible programs like slow compile times, buggy implementations, suboptimal diagnostic quality, poor debugging experience for optimized code. Okay. Okay, interesting. So we soon realized that the compiler industry as a whole has a similar problem, where existing systems like LLVM are very successful at unifying and integrating work across a range of different language implementations. Right? So think about it, right? So typically when you're programming here, so even because we generally work even higher level, right? We're usually just here. And then this is just your regular TensorFlow code. Your regular TensorFlow code gets turned into this graph. And then depending on the type of device that it is, it ends up spitting out its own intermediate representation. So then specifically the intermediate representation, let's say for the TPU, is different than, let's say, stuff that generally around on GPU, and even for TensorFlow Lite and CoreML, which is like the mobile alternatives for this stuff, also use their own compilers. And so this generally sucks, right? Because imagine if, let's say back to the analogy of C, where instead of just using something like GCC, you had to use 10 different compilers, each with their own feature sets, each good and bad at various different stuff. You're not going to get all the benefits, and just unifying everything takes way too long. All right, so Oh yeah, like this is so yeah, so the camera effect is with the here like the NVIDIA, like here this is like NVIDIA broadcast, so it uses a GPU to basically make the nice effect. So it actually looks even nicer if you show everything. It looks nicer, but it like makes you lose out on some of the space. Uh, like that could go to the image. But yeah, generally I would say this is probably one of the most useful GPU app because usually you would need a green screen to do something like this, or you get like a very fancy camera. Now you can just do it with the GPU. Um, so let's see the Swift AST and then the Swift Intermediate Language IR. Okay, I see. So this is interesting, right? So typically here, uh, all of these languages here, like, yeah. So this is Clang, right? So this makes stuff a bit easier, right, for these kinds of languages. But then everyone else has their own intermediate language, and even you can see it, like let's say in languages like Julia, for example. Sorry, I'm losing my voice. A second. So the point here is that someone is maintaining all of this shit. Yeah, so what are we reviewing? So we're reviewing this paper called MLIR, a compiler infrastructure for the end of Moore's law. And the problem that we're discussing is this. Basically, when you write a neural network, like let's say in something like PyTorch, where you just have this init layer and this word layer, you generally worry about like how good is the test performance? Is it explainable? But library maintainers care about like does it run fast? I think is the most important thing they care about. And this has two aspects to it. The first one is how does it run on a single machine, like with an IR, and then how does it run on multiple machines when given layers don't fit in a single network. The point I want to try to make here is that this sort of intermediate representation gets very complicated because even something like just think I want to run a model involves all sorts of complicated stuff where, like what are you actually sending to the GPU? What are you getting back? Like where is everything? Like what about like let's say in the case of embeddings, those aren't typically sent to the GPU as well because they're too big. So all of these stuff is generally abstracted away, and so I want to sort of peer open this black box so we can understand a bit more how these libraries work. Broadly, a customized insurance system can adapt changing requirements. Okay. Control flow graphs, instruction level, all without hoarding. Okay, sure. The static single assignment region form is a widely used representation in compiler IRs. It provides numerous advantages, including making data flow analysis simple. I actually got a recent bug like this about nested regions. I wonder what this actually means. Let's see. What is up with this nested regions? Thank you for the subscribe. Oh, Kuma Bear. Thank you so much. All right, so I'm trying to figure out like what this whole business about nested regions actually means in compilers because I actually did run into an error like this at work and I couldn't really understand what it meant. Okay, so you can have. Oh, interesting. Yeah, hey Kuma Bear. So the IR is recursively nested. An operation can have one or multiple nested regions, each of which is actually a list of blocks. Okay, each of which itself wraps a list of operations. Huh? Nested region. So a region has a list of blocks, and a blocks has instructions. Like, so why do you need blocks? Yeah, but so this is what the IR looks like, by the way. It looks a lot like regular, like assembly. Uh, you can read these. Like, okay, this is the type of this thing. You probably wouldn't want to write this. I guess these are registers here directly. I'm just saying what the type are. One nested region with one block with 0 arguments, 3 operations. Okay. Oh. What is this giant image? Okay, so block has some operations and some arguments. Okay, so it's like a part of a graph. That's fine. I still don't explain what the region is. User specifies an end before begin to teach it. Thank you, Habib. So our regions seem to just be a container for like a bunch of different operations. Like, I guess independent ones. This is actually like the LLVM source code looks like it's here. I don't know it was on Fabricator. This is a surprise to me. Example of nesting regions of overlapping regions. Again. Oh, I see. Okay, I see this. Okay, yeah, the terminology is actually very clear here. So, like, let's say you have two different programs. They're nesting. If they see here, this finishes, like bar finishes here, and then foo starts here and foo ends here, right? Versus overlapping would be for bar, foo bar. And so, oh, I see. It wasn't possible to have overlapping regions up until recently. You can sort of see why, right? Like, this feels kind of weird from a control flow perspective. But anyway, I think we're fine, so we can keep going. Here, let me just close this. All right. IR validation. Okay, so operation op is the main entity in MLIR, and it contains a list of regions, and regions contain a list of blocks, and blocks contain a list of ops, enabling recursive structures. So, okay, so they're saying here this is a region, and then this region can also has a block, okay, and there's another block. Yeah, like the nomenclature is like fairly abstract, honestly. Like I'm sort of like they just like say, I guess it's just something like I want to get back to. Let me just write down some notes for myself. Right, so basically understand region versus block versus ops. All right, so Defining representation modifier should be as simple as that of new abstractions, yes. Source, location, and traceability. Sure, yeah. Tracing and lowering. How long have I done machine learning? Let's see. I've been doing machine learning, I'd say, for 10 years now. I started off by myself at grad school at UC San Diego. Then I worked at Microsoft for 4 years. Then I had my own reinforcement learning company for 2 years. And right now I work at GraphCore, which is a company that builds a chip for AI, essentially called an IPU. So yeah, like a pretty long time. At GraphCore now, I mostly work on like graphs and transformer networks. So I've worked with a bit of everything, honestly, and I'm also feel free to ask me anything. I guess like a lot of the people that are old to this channel are pretty familiar with that. This is a pretty ouch. Tea burned me. This is a pretty open forum. Like feel free just to ask me anything. So okay, ops. I'm polynomial multiplication using affine and STD dialects. I wish they would explain what a region is exactly. Okay. But it looks like an op is like sort of a tuple for all the data that it needs. Location information. Yeah, like I think what's gonna end up happening with this paper, like all the other ones are like there were 4 papers I wanted to discuss today. SSA, control flow graphs. I think control flow graphs are sort of like computational graphs, but for regular programs. What's SSA? SSA is functional programming. I feel like we're about to go on a deep end right now. Yeah, so this is what I was saying with the control flow graphs. This is a nice paper, actually. Looks very clean. But basically, you can see how you can take a program like this and turn it into computational graphs. So I'm 17 and I'm trying to break into the field. If you were me, what do you think you'd be doing over the next 5 years? So I think like you should take any advice with a grain of salt. Like for all you know, like you're a lot smarter than me and you'll make better choices. But I would generally say for me the big thing. I actually wrote a lot of this stuff down. So yeah, I had this article here, like how to get a great job, that sort of describes my thoughts briefly. I will generally say is that this, like basically when I was growing up, like so when I was 17, the internet wasn't like this big of a deal. Like as in like yeah, people knew it existed and people knew that Wikipedia existed, but people didn't view it basically as a replacement for CVs or as a way to get mentorship, as a way to get coached, as a way to write software. And so I would generally say is like this is gonna sound very vague, but it's sort of on purpose because you need to think about what is interesting to your career. Is pick a few topics that you're really interested in, that you're obsessed about it, and then make lots of public content about it. So like let's say make videos, make tutorials, make GitHub repos, make YouTube videos, make Medium articles. So anything where that forces you to go in public is great because it lets you meet people that think like you and it forces you to make your content better. I would say the biggest counterproductive piece of it, like sort of a weird piece of advice, is I often feel like preparation is a is a form of procrastination to some extent. Like, let's say it's fine to be learning stuff for a couple of weeks, but if you see yourself learning for months at a time without producing anything, it generally means that you're doing like an intellectual version of procrastination. So try to avoid that. And just, like try to make interesting friends, right? Like, I think the people still use the internet, I feel, in a very limited way. But if you can figure out how to meet people that are interested in the same kinds of stuff you're interested in, I think it sort of like multiplies the power of the internet. So yeah, I hope that helps. Like, if you have more specific questions, I can answer that. But a general answer like what should I do for the next 5 years? Like, well, you're gonna get a general answer from me back as well. I don't know, because some of my advice isn't necessarily even programming focused. Like, some stuff is uh, like, learn what money is, for example. Like, don't just like put your money in a bank and think you're gonna get rich that way. Uh, like, there's many small things, like like invest in a good partner. Yeah, I have a whole blog post about the publicizing content. I think it's a game changer if you do it young, because basically, I think that especially now with remote work, like, you pretty much don't exist if you don't have an online presence. Don't treat life like an optimization puzzle, I think, is another thing. Like, I feel that's extremely counterproductive piece of advice, where people sort of try to put their head down and just like bully themselves into submission to do something that they think they want to do. Uh, I generally feel that procrastination is information. So if you find yourself procrastinating a lot on something, it often means you don't want to do it and you need to do something else with your life. So I think that's another big part of it. Single of the program with original placement of these functions. Okay, I still don't get what the fuck SSA is. Okay, I get this control flow graph. There are too many variables. Oh, I see. Oh, interesting. So it seems to be something about like intelligently reusing variables. All right, wait, where was the paper? Keep losing it. Okay. So I think this is what's gonna happen with this paper is I'm just gonna make a list of stuff I don't understand. I may need to do like another whole tutorial on it, and then we can cover other papers that are a bit simpler. Okay, so see dependent versus non-dependent types. Uh, Actually, I do want to add one more thing to the advice. I think like being financially independent young is very important. Like really this idea of yeah, you want to optimize for the stuff that you're learning, but like just having the flexibility of learning whatever you want without having to worry about money makes you a lot smarter, I think. Otherwise, you're sort of like constantly in panic mode and have to take uh, sort of suboptimal decisions just to survive. This is largely dependent, I guess, on where you're at in life. Like, I don't know if you're rich, if your parents are rich, if you know how to be rich, but this is just like something I think to think concretely about. And I think like publicizing work is like a very easy hack to slowly get there. The pass manager, okay. Okay, so this is back again, this idea of figuring out how to compute stuff like how to compile stuff on multiple machines. We sort of touched on that initially, so verifiers. Oh yeah, great, applications, right? So one application is Tensorflow Graphs. So where's the graph? Read variable, an addition operation, an assignment, and an addition. Right? And even though this looks kind of complicated, really what's happening is you're adding something to something else. So you'd expect to see two values. These two values are tensors of float 32s, and then they also return a float 32 with some control flow. Polyhedral code generation. Why do I feel like I'm sort of like tickling the the boundary? Polyhedral code. Lol. Let's do some googling. Polyhedral code generation. The order of loop iterations in the type system. Okay, so polynomial matrix multiplication using MLR affine dialect. Okay, so we have two nested loops. And then in one of the loops, we load A, we load B, you load C, and then you store. Yeah, so you see here, this kind of just looks like regular code at this point. Polynomial matrix multiplication kernel. So nothing like too crazy going on here. And so I wish they picked more complicated examples. This is just basically add, like also fairly simple. Okay, yeah, Fortran, famous Fortran. So one thing people don't realize is like actually when you're writing TensorFlow or PyTorch code today, you're probably using Fortran at some level of the stack. And essentially, it's just like because a lot of the Fortran libraries for numerics are just like very highly optimized. So we still use them. Like, lattice regression. Okay, so they're saying, okay, we have reusable compiler, privileged operation hooks, optimization interfaces. Interoperability. Okay, and they're saying like we want this to work with more languages and more dialects. So let's see. One thing I want to check about. Okay, so basically the thing about regions, uh, I think region means a sequence of code blocks and figuring out what can be executed concurrently or in parallel. I wonder if I should just like, maybe I'll do this actually. It's gonna seem weird, but like fuck it. The compiler. Trying to. Found a lot of terminology using dependent types, polyhedral, code generation, regions, blocks, verifiers. Any suggested teaching words? So I can understand everything. All right. Hopefully this works. I think. Like the thing is, like the issue with ML compiler stuff is I don't usually know that many people in person that do the stuff, so I legit don't know who to ask. All right. So I think like we're just gonna cut reading this paper short since it's insanely dense, and I think I'd benefit more from reading like some sort of compiler book at this point. Uh, so I think these are simpler. Yes. All right. So here we're going to talk about device placement. So this is sort of like one of the rare applications of reinforcement learning that make money. So let's just like go. That is a great idea to write personally in Twitter. Yeah, I do this quite a bit, like, because often, like, I just like, I mean, if he doesn't answer, I don't lose anything. But you know, hopefully, hopefully he does. Well, generally, I find like people are open to good questions. Like if it's clear, like if he can reuse the question, basically, uh, then it's fine. If it's sort of personal stuff or like like hey, do you want to chat? That's when people sort of tense up and they're like, go away, like I'm too busy. So the past few years have witnessed a growth in size and computation requirements for training neural networks, and they use heterogeneous compute on CPU and GPU, and they propose a method that turns to optimize device placement for computational graphs. Is the use of a sequence-to-sequence model to predict which subsets of operations on a TensorFlow graph should run on which available device. The execution time of the predicted placements is then used as a reward signal of the then it rewards it to optimize the parameters of the sequence-to-sequence model. So our main result is that on inception v3 for ImageNet classification and non-trivial that perform handicap heuristics or traditional algorithmic methods. All right. Okay, so here they're giving the regular spiel. Models are huge. You know, ML's amazing. That's what whole ML paper intros are like. Well, here's the thing. Like, I think that so Christian's making an interesting point. He's saying, so that's a great thought, but whenever I read a paper and I don't understand it, I'll be like, what if my question is too dumb? And so I think there is sort of an art form to asking a question, right? I think you sort of have to put yourself in the other person's shoes. What people hate, you know, like is sort of feeling like you didn't put in the effort yourself. Like if you basically say, I didn't understand this, like can you explain it to me? People tend to not appreciate that. But if you're like, well, like look, there's these parts I didn't really understand. Do you have like any references that would help me understand this? This is an easier question because then they just have to give you links, right? Like they can be like, sure, you know, here's 4 links, and that's it. Basically, you're trying to make it, like you're trying to make it easy for the other person to help you, because the more obstacles you use, the less likely they are to respond. And the more famous they are, the less likely they are to respond as well, right? So if you're asking, like, let's say, I don't know, Jeff Dean for a question on Twitter, it should also be like very clear and easy. Otherwise, he probably sees a lot. So the person usually has to feel that they're going to derive some value from answering the question. But otherwise, I would say this idea of a question is too dumb. It's interesting because I used to think that too, but I've often found like the more I've gotten deep into ML, like a lot of the basics, I would say are not that basic. Like they're not obvious why they're like it's not obvious why something is true. It's sort of like you believe it because this is what you've seen in textbooks a lot. And so I generally find those questions interesting. Depends on the audience, right? Like let's say someone's a YouTuber, like you can ask them like, look, you know, can you do a video about this topic? You know, because like I'm trying to understand it. If someone's a writer, same thing. If someone's very famous, you know, like maybe just try to be more mindful of their time. There's an exception to this rule. Like if you work at a company, I would say there's no dumb questions. Like legit no dumb questions because there's a lot of people use a lot of abbreviations. Processes don't make a lot of sense. Code may not always be very well documented. So internally, I think you should, you know, just ask away and not feel bad at all. Obviously, like do that more with your peers or like on a public Slack channel or something. But don't like just, you know, I don't know, email the CEO and ask them a question because then you're falling into the same trap, right? Where it's like, well, it needs to be worth their time and they need to be able to give you an answer easily. So they're saying we find non-trivial placement, and they're saying it's been used to optimize system performance. Okay, so what's the method? Like blah blah blah. So we have a TensorFlow computational graph with M operations and D devices. Okay, so a placement is an assignment of an operation to a device, sure. And so find a placement such that the execution time is minimized. All right, so let's look at this thing. Zoom in a bit. So type, output shape, okay. And then we have some hidden state, we have some attention layer, and then we have a softmax. Is defined as an attentional sequence equal to model. Okay, they learn it via Atom, no one cares. Yeah, so this is what I was talking about earlier, where you may have like a single layer that's bigger than a device's memory. So let's say in this case here, like let's say this layer is 40 gigs in size, right? Like you made it like let's say You just said like layer 1, and then you said, you know, this, boom. Like, how do you fit something like this on a single GPU? Okay, so they use a sequence-to-sequence model of the computations to the okay, so they take the so I think what they do is they take the computational graph, right, and then they feed this to a sequence-to-sequence model, and then they get back a placement, like, which they can fix the signal for using reinforcement learning. I think this is what the full pipeline looks like, but let's just confirm and read a bit more. Co-locate feature. Oh, interesting. Oh, interesting. It's 404s now. Okay, so check this trick out, guys. So if you ever have a link that 404s, you do this. Go to the Internet Archive, and then let's pick some sort of distant snapshot, like here. Aha. Right, so now we can co-locate an op, and then it's here. It's probably there somewhere. Anyway, so I guess like here, all they're trying to say is that you want like let's say you want the feature like you want layers that talk to each other very often to be co-located. So then distributed training. Okay, so this is just like data. This is called data parallelism. Like the difference here is, like let's say you have you can run a model on a single GPU, but you like when you buy a V100 or rent it out on AWS, you can only get 8 at a time. And so if you have 8 of them, instead of splitting the model over 8 GPUs, you run one model on each of the 8 GPUs. But then you have a central parameter server that does the so this is called like data parallelism or replicated modeling. Very useful. Like I mean, I would say it's almost like a standard because you just typically just change a couple of lines of code to support this, and you can say I'm doing multi-distributed GPU training. Like, that sounds cool. Okay, so where do they describe how the algorithm works? Then cut. Okay. The Scotch static mapper. This is how you know this shit is legit. It's like these like old ass websites. Okay, from Andrea, of course. It's probably Andrea. I would say the French university I see the most mentioned online by far, and one of the most commonly mentioned French European universities. Okay, so it looks like it's a way to partition graphs essentially. So I guess like doing all the splits. Single CPU, expert design. Okay. Okay, so then they're saying our running time was better. they ummed. Okay, interesting. So here they're showing like how the device placement actually works by color. And so let's try to see if there's any sort of pattern that we can extract out of this. So first off, it looks like there's how many colors? Like one, two, three. I believe there's four, right? Like green, red, yellow, blue, right? And so what's happening is that like blue talks to red, and then here like the green. I don't see a pattern like unless like I'm mistaken. I keep seeing these like red lines like this, like this. This one's interesting. So again, there's four GPUs. Yeah, this one is sort of interesting. Like, there's some like imperfections, but generally what I see it doing is that if there's three paths for the data to take, then each path is on an individual machine, and that would seem to make sense, right? Because like, you aggregate them and then you collect them in some central place. Uh, so here they're saying, okay, well, initially collect them in red, then collect them in green, and here when green is doing most of the work, then you have a green here. So and here there's mostly so whatever. It's interesting. Like it's hard to really figure this out because it's machine generated. It could be let's see. What the softmax takes this long? Okay, conf to D and average pool. All right, let's go back here and check one thing. So where do they describe the full algorithm? Okay, so they say we're trying to minimize this objective, and then to get the gradient for it, based on policy gradients computed via the reinforced equation, and then they estimate this loss by taking k samples leading to this using a baseline term b. Oh, I see. Yeah. So it is like this. Okay, right. So what they do is you. Okay. But wait, why do you need reinforcement learning? Because like let's say you try k placements, and then for each one you compute the amount of time it takes, and then you pick the best one. And see, minimize the objective. RP. So what was RP again? Okay, sure. They pick the square root of the running time instead. Whatever. Uh, so running time given the placement G, right? G is the placement. Yeah, G is the placement. And so the expected, okay, so the expected running time of the algorithm given the placement such that the placement is generated by a policy which takes in the placements and gives you a running time. I see. Oh, like an estimate for it. Oh, I see how this works. Okay, sure. Like your loss function is basically how far off you were from predicting the right runtime, right? Like you're saying, okay, well, I believe the runtime is going to be this according to my model. And then eventually, if you basically train a model that can, given a placement, predict a runtime, you can then ask this model, give me the best placement. So this is how this whole pipeline works. Okay, this makes sense. And so I like these graphs a lot, actually. This is very cool visualization. I think like what I find interesting about this, right, is that like let's say so here, for example, we took in a case where you have two layers, but let's say you had like 1,000 of them, right? Like let's say your forward uh, function looks closer to this, like you have to define forward, and then you basically say for layer I in layer x equals layer I of x, and then return x, right? And then you have something like, yeah. So by devices, we are talking about actual CPU, GPU devices. Wondering what are the real world use cases for this? Yeah, this is like, by the way, this is not like navel gazing in any way. Like this is very useful because the devices you're working with are either CPUs or GPUs or whatever other accelerator you had. Let's say you had a whole bunch of them, but you also have a model that you have. Like let's say you have ResNet 50 or Inception V3 or something, right? So the question, I mean, like maybe like I think I can make this clear. Let me show you what Inception V3 looks like in Python. Right, so this is what Inception V3 looks like. You have these conv, then a padded convolution, pooling conv, these inception networks, pool, linear self-mesh, right? So you have like all of these. And so the question is, let's say this doesn't fit on a single GPU, or you have more GPUs available and you'd like to use them. How do you distribute each of these layers on the different devices such that the running time of the model is minimal? So it's like it's like like an optimization problem, like literally, like you're just saying like minimize running time such that memory is less than like total available memory. All right, so going back here, I think it's enough with this paper. I think we sort of get the main idea. So let's go on to the third one, and we'll see. I'd be surprised when we go through 4 papers in 2 hours. Let's see. Look at why not. Okay. So let's see. So this is also a Google paper. Of course it is. So most compilers for ML are needed to solve many compiler-related optimization problems to generate efficient machine code. Leads to optimal solutions for neural model architectures, learning literature, sample efficient, transferable deep reinforcement learning method for computational graph optimization based on scalable sequential decision attention over an inductive graph neural network. Okay, this looks like very similar to the other paper. Mesh TensorFlow. let's check this out. Okay, so it looks like a DSL that does this kind of stuff. I don't think you generally need this stuff because I think with TensorFlow and PyTorch, you can just use these width scopes to do this yourself. So I don't see why a library would help. I could be wrong. Let's check an example. Yeah, this is a pain in the ass because like, you can't just take a regular model and just port this. Like you're doing all these hooks and everything looks so different. Like the way this is actually done is very simple. Like I'll even show you the code, right? Like you would generally just say this. You would say, like with torch dot device, and then you would say GPU 0, and then here you would say with torch dot device GPU 1. Boom. That's it, basically, and then here with torch dot device CPU. Like that's it. I don't get why you need a library for this shit. Like this is so much clearer. You can port code. You're using base libraries. You're not like porting your language to like yet another like domain specific language. And they've just made it very easy. Like I mean, this is not a huge deal. Like and this is basically doing, this is an example of what's called model parallelism. As in, you have a single model that's way too big. How do you make it fit on multiple devices? So it's simple. So, and really what we're doing with these the device placement papers, figuring out like, well, where do we add these lines, right? Like, because, like, would it be better to have this on GPU0? What if you had a single GPU? Then, what would be best to do? Would it be best to run both of these on GPU or one of them and the other one on the CPU? But if you had one GPU but a billion CPUs, then what would you do? So this becomes hard. I think you need lots of domain knowledge to figure it out. So I definitely... I'm very optimistic about compilers just solving this problem for people, because this seems like a machine-specific thing that's hard to figure out by yourself. Let's go back here. Okay, so they're defining the problem in the same way. Okay, we have a data flow. Okay, they also add this thing called op fusion. Yeah, so basically, can you merge something into one function? Like, again, let's say back here. This is a pretty cool example at this point. So let's say here, like you had, x equals layer 1x, and then x is equal to layer 2x. Well, you can rewrite this as x is equal to layer 2 of layer 1 of x, right? So then basically you're basically doing function composition, right? You're saying like layer equals layer 2 of layer 1. I wonder, does this just work with Python? I forget the function composition in Python. Actually, maybe, yeah. Yeah, you can do it with lambda functions. Yeah, like this is what I mean here. That's why I was wondering if it just works out of the box. But this certainly works like this. You just, like, let's say here, they're saying you have this function called double and this, and then you say compose, and then you give it the actual output you need. FuncTools has something like this. Yeah, okay, see? So what the star means here in functions, it's it's unpacking a list, right? So what this does is it turns a list into a bunch of elements, and so then you basically compose all of the elements one by one. Yeah, it's similar to currying. So currying means partially applying it. But yeah, like you're correct in thinking about currying here. So where were we? Okay, so here they're doing multiple data flow graphs. Fine, if you have multiple data flow graphs, it's like having one giant graph. Like, I don't see why they even need to mention this. Multiple tasks jointly also doesn't matter, right? Like, what is the total running time for the whole thing? Doesn't matter how many loss functions you have. Okay, so graph that combines graph embeddings and sequential attention. So node embedding, state embedding, segmented transformer layer, input feature conditioning, segmented transformer layer, and then you get a policy output. Ops type, output type, input ops. Then aggregator, okay. So the difference really seems to me to be this, right? Like in the other work, they used basically an LSTM that is fed in the graph representation, versus here they're actually using a GNN instead. So it's a sort of very natural improvement. Uh, and so what do they do with it? Okay. Having multiple policies has zero impact. And then they show the performance running time versus a whole bunch of other models on each of our workloads. Op fusion, generalization, and cross. All right, okay, so this paper is identical almost to the other one, right? Like the device placement. I mean, it's not the same people, but it's also Google people. And I will say the difference is basically instead of using an RNN with attention, they use a GNN with attention. So they're actually almost identical. They claim that the scope is a bit bigger, but to me, I don't see why the other approach wouldn't work just fine. Maybe it didn't scale. I think it is one of the issues. So maybe the biggest contribution here is more experimental than it is theoretical. But conceptually, the idea is the same, right? And that you try out like a certain like you take a given placement, you try to predict the amount of time it takes, you look at the difference between the time you predicted and time it actually took, and you use that to basically update your the estimates of your network. So we have one more paper. Our tasks. Okay, so this is MSR people. Looks like MSR China. Peking University, Shanghai Tech. Okay. Let's check this out. This will be, I think, the last paper we discussed today. So performing deep neural network computations on hardware accelerators efficiently is challenging. So existing DNN frameworks and compilers often treat the DNN operators in the data flow graph as opaque library functions and schedule them onto accelerators to be executed individually. We propose a rammer, a DNN compiler that optimizes execution on massively parallel accelerators. Static spatiotemporal schedule for DNN at compile time to minimize scheduling overhead. Maximize hardware utilization by holistically exploiting parallelism through inter and intra-operator co-scheduling. This was a much richer scheduling space for multiple NVIDIA AMD GPUs and GraphCore IPUs. Oh, interesting. I should ask who among my colleagues here, like. It's a nice, pleasant surprise. Okay, well, let's read this. Okay, so here, like, I think their approach is fairly different, right? So they basically come up like with their own like virtual machine where they can abstract away machines and then schedule stuff to them. So sort of treat it like a black box. I mean, yeah, like this is sort of like well known, I guess. Like typically, whenever you're doing stuff with smaller batch sizes, your device utilization is going to be very low. And so with GPUs, typically people increase them to like absolutely ridiculous degrees. Although like the research keeps going back and forth on this. Like I've read a bunch of papers saying like small batch sizes are better, and it's just a question of not finding the right hyperparameters. Okay, it's like way too much like terminology in this paper. Like the R task and R schedule and R order and R virtual device and R waiting and R task and R UID and R wait and an R barrier. It's a bit confusing to figure out what's going on exactly. But let's keep going. Okay, sure. Show you an example. DFG compiler kernel. I was gonna write this note to myself. So I think like it looks like basically in a block, in a GPU block, number of threads is usually fixed. Okay, so sorry for the long pause, everyone, because I was just trying to read and get some sense of what's going on. Okay, so I think like really my take of what this is doing was that like they basically have their own like given so given a DNN, like a static DNN, they transform it into their own intermediate language, which they then figure out how to optimize efficiently for various devices and implementations, etc. So in terms of benefits, let's see. So they're saying like, okay, well, we have like this 50K compile. Yeah, so this is the main. I think the main idea is here, like this picture here. So this, it's like you have a DNN model, and then you turn this into a graph, and then this graph gets like it passes through a compiler to give you a program, and then generates some specific device code. And there's some hand-tuned kernels here to make all of this run fast. Which is pretty interesting. And then I think the main thing they talk about here block. And I think like let me just Google this like GPU fixed block goods. I think I may have Googled this earlier as well. Okay, so the grid of blocks and thread blocks can be 1 or 2 3-dimensional. Streaming multiprocessors as a set of execution units, a set of registers, and a chunk of shared memory. A warp is a collection thread, 32 execute bytes. When a CUDA program on the host CPU invokes a kernel grid, the blocks of the grid are enumerated and distributed to SMs with available execution capacity. The threads of a thread block execute concurrently on one streaming multiprocessor, and multiple thread blocks can execute concurrently on one. As thread blocks terminate, new blocks are launched onto the vacated streaming multiprocessors. Oh, interesting. So blocks share. So it's like similar to the way like it works in a regular CPU. namely in video streaming multiprocessor, as many programming parallel paradigms. Okay, so the number of the threads in a block are fixed over the lifetime of a program, right? And basically just set it to the maximum of what you need among all the operations. Yeah, so I think that was it, everyone. Like, I think I have like a couple of more stuff I want to research, I guess, for maybe a future talk around like SSAs, control flow graphs, like verifiers, polyhedral cogenerations, regions. But overall, like I would say, like maybe we can just do a quick scan of all the papers again and just give them a high-level summary before we can call this. So like this was the last paper we discussed. So basically what they do in this paper is given a DNN in some language, you create a language on top of it, which you can then create your own optimizers for various hardware accelerators. And they use like a bunch of different hardware here. The other paper was MLIR. So this was the most complicated paper. It takes a very similar approach, but discusses it really more from the compiler's perspective. As in, you have a DNN in some language, you turn that into a graph, and then that graph you turn into MLIR code, and this gives you all benefits when you're trying to speed things up. The third paper we talked about was this paper around you basically given a model that you want to run and a sequence of and a bunch of devices, figure out how to optimally place all of these layers on multiple devices such that you minimize the running time. And the main model they use here is a graph neural network. And very similarly, this other slightly older paper on device placement with RL uses the exact same thing, but instead of using a graph neural network, it uses an RNN with attention. So I hope this was useful, everyone. I definitely want to expand this series because there's more stuff I want to talk about with optimizing this stuff. So perhaps like we'll just either go deeper into the MLIR paper, or maybe go deeper into that last paper by the folks at MSR. So yeah, I hope this was fun. If you have any other like suggestions for more content, feel free to let me know. And thanks, everyone.